Hey everyone, today we're going over our slinky drop experiment. We recorded a falling slinky, tracked its motion, and looked at why the bottom of the slinky stays completely still at the beginning. This phenomenon looks simple, but the physics behind it is actually super interesting. When most objects fall, the whole thing moves together, but a slinky doesn't do that. When you drop it, the top collapses downward first, while the bottom just floats in place for a moment. Our goal was to observe the behavior, track the motion, and compare what we saw with what physics says should happen. So we used a video that was already recorded, and we used a tracker to mark the bottom point frame by frame. Tracker gives position values over time, so it shows exactly when the bottom starts moving and how fast it moves. Our job was just to collect the motion and analyze it. To explain what's happening, we used the basic physics behind springs and forces. The force of gravity, F equals mg. Force of spring, F equals kx. And also there was a drag force. Air slows the slinky down as it falls. The faster it moves, the stronger the air pushes back. The equation is negative b times v, absolute value of v, power of 2, times v hat. Every coil is pulled downward by gravity. The slinky also pulls upward with tension, trying to keep the coil together. The tension fights against gravity and depends on how stretched the slinky is. So even though we didn't model anything ourselves, these equations explain exactly what we observed. Here's a graph comparing the predicted motion curve to the actual data. The flat part at the start is the bottom staying still, but both the theoretical pattern and the real data match this behavior. Once the collapse reaches the bottom, you see the sudden drop. The real and predicted slopes line up pretty closely. There are tiny differences, but the overall motion looks the same. Still at first, then fast downward movement. This is the coding that I've done. This was the tracker. The mass was 0.218 kilogram, drop height was 1.75 meter, initial position was 1.6 times 10 to the negative 3, 2.7 times 10 to the negative 4, and 0. The initial velocity was 0, 0, 0. Possible error. Tiny changes in slinky's movement could be caused by outside forces that our model doesn't account for. This can make the real motion slightly different from the predicted one. Possible error 2. When marking tracking points in tracker, they might not be placed perfectly due to human error. Even being a little off can change the recorded motion. Why does the bottom of the slinky stay still? The forces acting on the bottom of the slinky cancel each other out. Gravity pulls it downward, but the tension in the stretched slinky pulls upward with the same strength. Since these forces balance, the bottom stays still until the collapsing wave from the top reaches it. What if you attach a heavy weight to the bottom? Would it stay still? It depends. If the slinky is long enough or has a high enough spring constant, the tension can still match the weight's force. In that case, the bottom will stay still just like before, at least until the top collapses all the way down to the weight. Conclusion. In summary, my results show that the bottom of the slinky stays almost completely still during the fall. Both the tracker video data and my glow script model showed that the upward tension from the slinky balances the pull of gravity, which keeps the bottom from moving until the collapse reaches it. The small variations in this video were mostly caused by hair resistance and tracking noise. Overall, the real motion lined up very closely with what the model predicted. Thank you everyone for watching. It was James Han with a Lab 5 Slinky.